do the round robin and have people tell us where you are and what's the weather. So, Rosemary, where are you and what's the weather? What have you
Okay,
seen in the
I
sky?
am I am in Bayville, New Jersey, and the weather is overcast and about 25 degrees. So it's pretty chilly lately.
Not a
And
whole lot to see in the sky.
no, not at all. Not at
Jim,
all.
Jim, where are you?
Morning, everyone. I'm in Anthem, Arizona, about 30 miles north of downtown Phoenix. We had a lot of rain lately, and it's going to be about 69 degrees this afternoon.
Dennis.
I am in Denver, Colorado, where it's clear and getting up to the
There's
60s this
about
afternoon,
20 or
as it
30
has been
people.
doing all month. And I was up before dawn this morning and looked out the window and saw a big fat moon and Jupiter right over the mountains.
Fabulous. Chris, where are you and what have you seen in the sky?
I am set to Europe. Phoenix, to be precise, for the full moon rise over Convex Abbey here outside of Phoenix.
We can
Absolutely
talk
incredible.
because they can't hear us.
Right. Okay. Carmen, where are you? Oh, you're muted. Carmen, you're muted.
I'm sorry, I am in Uruguay, South America. Till yesterday, we have a gorgeous summer up to 35 centigrades. But
Oh,
yesterday
wow.
night, well, we had a huge storm, really huge storm. So I could see the moon among thunder and lightning. It was really beautiful. But
Okay.
now the temperature has gone down and the beach is completely flooded with the sea. So we
Hmm.
cannot go to the beach.
Oh dear. Stan. Oh,
Philadelphia 30 and overcast.
fabulous. Pam? Okay, you're still muted. Still muted. So can't hear you. Okay. Phil Smith.
Hi, I'm in Eastern North Carolina, New Bern. Um, got to see a few mornings ago the International Space Station fly over early in the morning, and it was like the largest Jupiter, and it was very
Mm,
nice viewing.
fabulous. Linda and Paul.
We're in Allentown, Pennsylvania, um, and we had a lot of ice and snow, and we actually saw the full moon. I think it was at 2 a.m.
In between a break in the clouds.
All right. Okay, Francis.
Hi, 26 and cloudy in Davenport, Iowa.
Okay. JP.
Hi everyone, I'm in Phoenix, Arizona. It's 15 degrees Celsius right now, a little overcast, but yesterday the moon was beautiful. Yeah, very nice, clear night.
Okay.
And I think I saw a launch of a SpaceX toward the west yesterday night. If any of that.
Bob also saw that. I was going to ask him about it, but yeah. Bob, can you tell us what you were heard what it was?
Well, yeah, I was told it was a Falcon 9 booster, but it was quite spectacular. It looked like a
Yeah,
comet.
yeah, it
So
was beautiful. Yeah.
I took a nice photo of it.
Mhm.
Okay, Katie.
Good morning from Pasadena, California, and we're waterlogged. It doesn't rain here very often, but it's been raining and raining and raining, and I'm a block away from the Rose Parade, so it rained right through that, and it's been a mess, but it's good.
Okay, Diane.
Hi from Sioux Falls, South Dakota. It's about 30 degrees with a little snow on the ground.
Fabulous. Sonu's just iPhone, and if you can speak, great. If not, we'll move on. Okay, Bob Trembley.
Hi, I'm in northern burb of Detroit, and it is 20 degrees Fahrenheit and a little bit of snow on the ground and overcast.
Okay, James.
Hello, I'm in Southington, Connecticut, and it's 30 degrees and cloudy today. And on this Feast of the Epiphany, I've been working through Michael Molnar's book, The Star of Bethlehem.
Fabulous. Deanna.
Do you mean Dina?
Dina. I know you.
Yes.
It's Weibel at least, and not
I'm
Weeble.
in Grand Rapids. It's about 25 out, and it is currently snowing. And the last time I can remember seeing the moon, it was a crescent. So it's been cloudy for a while.
Okay, Larry.
This is Larry Lebowski. I'm north of where Guy is right now, and I would assume where Paul Gabor is. It's almost 50 degrees, supposedly getting up to 70 something, and did see the moon this morning.
Yep. Gary.
I'm in Milwaukee, Wisconsin, and it's been pretty.
Oops, you just went off.
It's been pretty overcast. It's about 20 degrees here, but last night did see the moon through high clouds.
Fabulous. Bill.
Good morning. I'm in Aurora, Illinois, and it's overcast and about 24 degrees. And my holiday travels have taken me to Peoria and Kalamazoo, and they were both overcast. So if this planet has a moon, you couldn't prove it by me.
Okay, from the tides in Lake Michigan.
We could check. I didn't think to check the tides in Lake Michigan, Guy.
Which I think Lake Michigan's probably frozen anyway. So, Joe.
Hi, Joe Stickney from Phoenix. As everyone said, it's cloudy here, but my concerns are more earthbound for our Venezuelan priest and the many Venezuelans he has in our congregation.
Indeed. Justin.
Justin, Watertown, Connecticut. It's 25 degrees, sunny, and 9 inches of snow on the ground.
Oh my, but did you get to see the moon?
It was beautiful this morning at 1 a.m.
Fabulous. Okay, well, welcome everybody. And we'll go from here to turn it over to Paul Gabor, who will tell us the latest on what's happening at the VAT.
Well, right now, nothing much. But we will be expecting another run starting on, what is it, Monday? Larry Lebowski. Does anybody know that guy? And Mark Trueblood and Robert Crawford will be going up. So that will be the first run of the year. Over the past month, we had another Lebowski run to begin with, which was, I think, mostly successful. But then we had, at a certain point, oh, that was the previous month. Okay. But still, I don't think I was able to join you last month. So let me report on that. Poor Jean-Baptiste went up for 6 nights, and he did not manage to get on the sky at all because of the weather. And then, Rich Boyle was very successful. He had, I think, a 12-night run and 12 nights of Christmas or something, 12 days. And he got 11 out of those with perfect weather and great seeing, sub-arc second seeing. So, generally speaking, things are moving slowly but steadily on the front of various upgrades. So,
Bob was asking you at breakfast this morning, what would happen if Jean-Baptiste and Rich Boyle went up to the telescope at the same time? One of them always gets clear skies and the other always gets clouds.
I think it would be a system error. The weather system error, a situation like this. But I don't know. It could be that this is just coincidence. But after all these years, I'm not entirely sure. There might be some causal link between these people and the weather. But who knows? Anyway, so we are moving forward with some actually pretty busy time at the VAT this month. We have some engineering time towards the end, but other than that, it's all observing with, as I said, the Lebowski run. Then Chris Corbley will go up. Then we'll have the NAU group, Northern Arizona University, and that will bring us to an engineering period with actually another couple of 3 nights, in fact, at the very end of the month, with Robert Crawford and Mark Trueblood taking some more donut data. And that has nothing to do with food. That's the preferred food of this group are not actually donuts, but not pretzels, bagels. So, I mean, it's similar shape, but I don't quite know what the astronomical significance of all that is.
Well, describe what the donut run is all about.
Well, if you take the telescope out of focus, but it is kind of well aligned, you will see a donut. And the donut, if you look closely, is actually an image of the primary mirror with the hole in the middle. So that's typically.
So you get a star that's out of focus, but in the middle of the out of focus star is the shadow of the primary mirror, or the secondary mirror.
Right.
Right.
So you end up essentially seeing these ring-like shapes, thick rings, hence the name donut, and you can use them to determine whether the telescope is well aligned or not. And in fact, this donut routine allows you to calculate exactly how out of alignment the telescope is. It's rather technical, but basically it's a nice quick way of getting the telescope well aligned. In our case, the telescope is absolutely crazy because of its primary mirror, which is basically like a salad bowl. So you end up having an extremely sensitive positioning problem. You need to place the secondary mirror exactly where it should be at about something like a tenth of width of a human hair. You can see the influence of such very small changes of placement of the secondary mirror with respect to the primary on the quality of the image. And yes, this is definitely a drawback of a telescope like ours. Now, the advantage and kind of the reason why the telescope has this primary mirror so deeply curved is because this allows you to make the telescope much shorter. So you don't need such a big building for it. Of course, we all love the classic big telescope buildings with nice spacious domes you can do concerts in, as Katie can tell us. But unfortunately, those things are very expensive. So the idea was in the 80s, let's try making telescopes that would be squat and therefore wouldn't require big buildings. So our telescope is kind of a prototype of that new approach to telescope building.
One of the other advantages too, isn't it, that you can cool off the air inside the dome very quickly, and that improves the seeing when the dome is small.
Well, I suppose it's one of these things that the dome seeing is more of an art form than science. There are people who have small domes and still have trouble with how to cool the mirror. But yeah, I mean, there are definitely advantages other than just the size. But the disadvantages are also there. Now, thanks to a positioning gizmo that we installed in 2017, we can actually do this in a nice and reproducible way. We can position the secondary mirror where we need it. It's just that we don't know where we do need it. So for that, we need to do these calculations with the donut, with our donut routine or some other tricks.
It's basically a piece of software that takes an image and then says, nudge the secondary a few microns in this direction.
that's pretty much it. 2 images is the minimum, but yeah, you got it. And generally speaking, we've been working with Robert Crawford, who is the primary architect of that piece of software, and with a whole group of people from the College of Optical Sciences who are trying to figure out how to optimize the process. So it's a very iterative thing. We go up there, we take some data, we improve something, and then a month later we can do another iteration. So if we could do this faster, it would be more practical. But we've been working at it for, well, pretty much 2 years now, because between iterations it's always at least a month.
I'm reminded of when I was in the Peace Corps a zillion years ago. There was my Peace Corps flag hanging up on my shelf there. I had a little telescope, a little 3-inch, smaller than Stan's 8-inch that he talks about in the below. And I took it up to upcountry for people to take a look at. And there was an old man who could barely speak Swahili. I think he just spoke Kikuyu. So I would speak Swahili to somebody to speak Kikuyu to him as he's looking through my little telescope. And he's looking at Jupiter and he gets this amazing smile on his face. So I asked my friend, I have to ask him, what did he see? What's so amazing? And the message comes back, I saw this planet. It was a giant ball of light with a big black spot in the center, which is to say that he saw the planet totally out of focus. And I didn't have the heart to try to fix it for him. So he probably went to his grave thinking that's what planets look like.
Yeah. Oh dear. That's a sad story.
Well, thank you everybody for coming here. I should also point out that one of the things when we decided to design the telescope this way with the very, very fast mirror, and then the secondary beyond what we call a Gregorian design, no one had ever made a telescope like that of that size before. And we weren't sure when we were making it if we would be able to focus it. Turns out we can. So, as Chris Corbally likes to say, we took a Gregorian chance. And I'm glad I'm on Zoom so people can't throw things at me. With that, it's my delight to welcome to the Zoom this month Bob Macke. Bob is, of course, well known to all of you guys. And I will start with basically just asking him to remind us who he is, what he does, and we will hear a specific story today about his life with NASA spacecraft. So, Bob, welcome and remind us again in a sentence or two who you are and what you do.
Who am I? That's the question I ask every day. So I'm Brother Bob Macke. I am the curator of meteorites at the Vatican Observatory. So my main job is basically to take care of the Vatican meteorite collection in Castel Gandolfo. I also do research on meteorite and extraterrestrial material physical properties. So that is density, porosity, magnetic susceptibility, and other properties. And so that's kind of my main area of research. And that particular expertise is sort of what got me sort of connected into space programs. So I think that leads Guy to his next questions.
Indeed. Now, we know that the NASA budget is 0.5% of the U.S. National budget, and the Vatican Observatory's budget is 0.5% of the Vatican City-State's budget. The countries being somewhat small means that we don't quite have the same space program at the Vatican that the United States government has. How did you first get involved in doing spacecraft work? How do you even learn how to become involved in spacecraft work?
Thankfully, just before I started my PhD program at the University of Central Florida, I was convinced by my thesis advisor, Dan Britt, to apply to the Planetary Science Summer School at the Jet Propulsion Laboratory. This is a 2-week program every year that is at JPL in Pasadena, California. And they basically, the whole point of the program is to really teach about creating space missions and mission proposals.
So this was
And
when?
so
What
this
year was
was in
this?
2007 that I did this.
Nearly
And
20
this
years ago.
program, yeah, this program brings together scientists and engineers. So yes, in fact, rocket scientists are involved to really talk about the mission, both from the science aspects and the engineering aspects. And so we, as part of the program, designed a proposal for a mission to Venus. And there were 4 scientists, and there are 15 people total, 4 scientists, and the rest engineers. So actually, we're very engineer heavy. So the 3 other scientists have all gone on to work in other missions. So they're involved in Mars rover, Lunar Reconnaissance Orbiter, Dawn, the Europa Clipper, which is planned to go to Europa, Dragonfly, which is planned to go to Titan, and others. And of course, I'm involved in OSIRIS-REx and Lucy. So so the program works. I don't know what the engineers are doing, but the most fascinating thing about it is, of course, the conflicts that we ended up developing between scientists and engineers. And by the way, our roles weren't necessarily all like the sort of roles we'd end up with in reality. Like I ended up working with the communications system, and so I was sort of communications engineer for that mission proposal. And the funny thing is, so information is a valuable resource with space missions because the data has to come through the deep space network, so basically transmitted from the spacecraft to the deep space network on Earth to be detected and received, and which is a series of antennas all around the Earth. And the data rate is incredibly low for the amount of data. So we had the scientists wanted terabytes of data, and the communications engineering could grant kilobytes. So you know, you had to be very careful as to what, you know, in your mission design, what goes into that. And you know, there are all sorts of other things we learned about, obviously, on a spacecraft, you want as many instruments as possible, but every instrument adds weight, complexity. There's this thing called technology readiness level. So it has to basically be demonstrated as something that's actually that you can actually put on a spacecraft and it'll work. And all this other stuff. And so of course, you shoot for the moon, you ask for everything, and you get like 3 instruments. Is sort of how things work. It's fascinating stuff. But yeah, we learned quite a bit, and I could talk more about some of the stuff we learned about spacecraft proposals from that.
A few of the things that
but
I remember hearing about in the 80s, there was a Mars mission that it was going to follow up the Viking missions, which had marvelous images of the surface of Mars, but nobody quite knew to any precision the relative altitudes or how high are the mountains from the plains, and is this plane higher than that plane? So somebody proposed a mission that would orbit an altimeter around Mars. And since you're going to Mars, you may as well have another thing and another thing and another thing. And eventually they ran out of space, weight, and money. And the mission, the instrument they threw off was the altimeter, the one that they had actually designed the mission for in the first place.
Yeah.
But
Yeah,
this
and
also
another thing is, I mentioned the technology readiness level. So one of the easiest ways to get an instrument on your craft is to say, look, we've already flown this on this other mission. But let's say this other mission went to Mars, and now you're going to Pluto. Pluto is 100 times farther away than Mars, and which the amount of light you get from the sun is it goes by the square of the distance, so it falls off by exponentially. So the farther away you get, the less light you get. So if you've got a camera that worked fine on Mars, you're not getting any light on Pluto.
Got to be sure to. This is the scientist talking. I think Pluto is 15 times farther away than Mars, not 100, but still.
Okay, yeah, whatever.
Yeah.
You know what I'm talking about.
and it's geometric, not exponential.
It goes by the square.
It goes by the square, indeed.
Yeah.
let's actually pull back a little bit. Who comes up with these ideas for missions, and how does NASA decide which mission gets chosen?
Well, who comes up with these ideas is basically the individual labs and institutions that propose the missions, but there's usually a call for proposals. So NASA kind of says, look, we've got a budget to consider one or two space missions for the next, decade or so, whatever their time frame is. And then so they send out a call for proposals and people put together their mission proposals. And usually is one institution that is sort of the primary sponsor. So the principal investigator represents one institution. So for OSIRIS-REx, it was the Lunar Planetary Laboratory at the University of Arizona. And for the Lucy mission, it's the Southwest Research Institute in Boulder, Colorado.
You and I both, of course, know very well a fellow who has been proposing missions on and off, your advisor, Dan Britt.
Yeah, Dan Britt has been involved in several proposals. He wants to do sample return from Phobos and Deimos because the expectation is that through various impacts on the surface of Mars, you have material being thrown up. So the surface of Phobos and Deimos probably is covered with at least some level of Martian material. So it'd sort of be a cheap and easy sample return mission for Mars. It doesn't involve actually going down to the surface.
There is, of course, a story dating from before you worked for him. Dan came and spent some time at the Vatican Observatory when we were setting up the density measurements. And this was back in the days when we were in the Papal Palace. And our offices are on the top floor of the Papal Palace, one floor above where the Pope resided. And of course, there's a 9-hour time difference between Castel Gandolfo and Jet Propulsion Laboratory. So he tells the story. He's in his office relatively late at night talking to people in the middle of the day at JPL. And the conversation, shall we say, is getting heated.
Yeah, because one of the guys was trying to hijack the project.
So Dan is getting quite furious with the window open in the evening when suddenly there's a knock on the door and a Swiss guard in uniform looks at him and just puts his finger to his lips and points downwards. At which point Dan had to
says,
restrain
I'll have
his
to call
vote.
you back later. I'm keeping the Pope awake.
So you were involved now in 2 missions. Tell us how you got involved in the OSIRIS-REx mission.
All right. So OSIRIS-REx actually comes specifically through my connections with the physical properties measurements. So OSIRIS-REx, by the way, is a mission that visited the asteroid Bennu and actually touched down on the surface and grabbed some material and brought it back to the Earth. So I was not actually involved in the spacecraft part of the mission at all. I am involved in the sample analysis team. So the material that came back to the Earth, I was involved in the team that studied that material. And so the mission launched in 2016. It got to Bennu in 2018, did the collection in 2020, and returned to the Earth in 2023. I got involved in the mission in 2020 when they were putting together the sample analysis team, and the head of the sample physical and thermal analysis working group, Andy Ryan, contacted me and various other people like Guy and Dan Britt to inquire about how to do the physical properties measurements, right? How, the density and porosity in particular. And so based on the advice that I provided, he just kind of said, you know what, I think it'd be easier if you just worked with us directly. So why don't you join the team? So I joined the team in 2021, and my specific role was to develop an instrument that would go into the glove box at Johnson Space Center to measure the density of these specimens in the glove box, so under pristine conditions. So I built an Ideal-Gas Pycnometer, which is something I've done before. I built one while I was studying theology at Boston College, because that's what you do when you study theology. And I'd worked extensively with them throughout my entire grad school career. So I knew the instrument inside out. The specifics about designing one for the glove box environment is it had to meet all of the very strict contamination control guidelines. So only very specific materials could be used. So I had to design everything around a very short list of materials. And the gas we used for the measurement was gaseous nitrogen. So I have to mention how ideal gas pycnometry works, by the way. So you have basically two chambers. It takes advantage of the ideal gas law, or rather Boyle's law, so constant temperature. You have two chambers. You put the specimen in one chamber, pressurize it, and then open a valve to expand the gas to the second chamber. And as the volume of gas expands, the pressure will drop by Boyle's law. And you compare the initial pressure and the final pressure, and knowing the volumes of your chambers, you then can calculate the volume displaced by your specimen. And density is mass divided by volume. So you already know the mass because you already put it on a scale. So that's the basic concept of how this thing works.
So you built this thing, you tested it out, and it worked?
The testing worked fine. All of the tests were perfect. But the proof is in the pudding, and when we actually put it in the glove box and worked with the Bennu specimens, we got something rather unusual. So the specimens came back, and we put them in the machine, and we were measuring densities that were physically unrealistic. They were incredibly high. They were basically, if the stuff was made of pure iron, then we could get densities like that. I mean, and they're not. These are phyllosilicates and other lower density materials. So it's we're getting 2 to 3 times higher densities than we should be getting. And it's like, what's going on? It worked fine on all the tests. We even practiced with a Bennu simulant that we had produced. Actually, Dan Britt had produced the Bennu simulant based on what we expected to find, I should say, because this was before the sample return, obviously, that we were working at that. So what's going on? Well, it turns out the very fact that we were keeping the specimens as pristine as possible, as unconnected with, and no contact with the normal atmosphere, was actually part of the problem, because these have a very high surface area to volume. So basically the structure is very fine-grained, kind of fractal structure on the inside. And all this extra surface area, the nitrogen would adsorb, would stick to the surface of that. And nitrogen could do that very easily. So when you take the nitrogen of the ideal gas pycnometer and you stick it to the surface, it ceases to be a gas. So it ceases to operate as an ideal gas. All of the calculations are assuming that the gas is a gas and it's behaving properly. So it stopped behaving properly, and so that threw all of the measurements off. Now, why didn't we see this with the analogous specimens that we practiced with? Well, not because they don't have that structure. They did, actually. They were very fine-grained and very porous. But they had been exposed to the atmosphere. And the moisture in the atmosphere, the water molecules, also adsorbed to the surface. And so they had stuck to the surface, and so they blocked the nitrogen from sticking. But in the absence of that, in this pristine condition, it didn't happen. And so the nitrogen stuck instead.
So you discovered something interesting, but just not what you were trying to discover.
Whenever you do space missions, you always have to prepare for the unexpected, even when you're dealing with return specimens. I mean, this is one of the lessons that we learn very quickly in any space mission is, whatever you're thinking to find, you're going to find something different, even bringing it back to the lab.
Okay, so you were also involved in another spacecraft mission. Tell us a little bit about the Lucy mission.
Okay, Lucy. I have to start with the naming, by the way. So OSIRIS-REx is this complicated name, and it actually stands for Origin Spectral Interpretation, Resource Identification, and Security-Regolith Explorer. So a lot of these space missions have these complicated acronyms. It reminds me of there's this episode of the show Agents of S.H.I.E.L.D., where somebody says, this is the Strategic Homeland Intervention Enforcement and Logistics Division. Do you know what that means? And the person said, it means somebody really wanted the acronym to be S.H.I.E.L.D. And a lot of the space missions are like that. They're named in very complicated ways because somebody just wants it to spell out something. Lucy is not an acronym. It is a name. It simply is Lucy. It doesn't stand for anything. Why is it called Lucy? It's called that because well, it's named after the Australopithecus skeleton, the Lucy skeleton that was discovered in Africa some time ago. That was, at the time, the oldest hominid skeleton that had been discovered. There have since been older ones. And that name, by the way, has its, that it's not named Lucy by accident. Actually, it is named Lucy by accident in a sense. But that's named after the Beatles song, Lucy in the Sky with Diamonds. Because the crew, the Donald Johanson and his team that uncovered the skeleton were listening to the radio while they worked. And it just so happens when they uncovered that skeleton, what they were hearing was Lucy in the Sky with Diamonds. And so the name of the song got stuck to the name of the skeleton because they would be like, oh yeah, are you going to go back to the Lucy site? And so the mission patch for Lucy has an image of the skeleton, but is also in the form of a diamond. So yeah, but the whole point of Lucy is it is going to the Trojan asteroids. So these are asteroids that are stuck they're kind of trapped in the Lagrange points in the orbit of Jupiter around the sun. So it's 60 degrees ahead and 60 degrees behind the orbit of Jupiter. And they're trapped due to these gravitational stabilities in the Lagrange points. But the expectation is that these were trapped early in the history of the solar system, and that the population of asteroids that they came from was otherwise ejected by other interactions with Jupiter that threw things out into space. So that these are sort of a missing link in the asteroid population and in the history of the solar system, which is why the name Lucy is sort of because we expect them to be a missing link. And so the mission is actually, it's not going to visit just one asteroid, it's going to visit several. On its way out, it's already passed by one near-Earth asteroid and one main-belt asteroid. The near-Earth one was just sort of a lucky chance. It was the asteroid Dinkinesh. And then the main-belt asteroid is the asteroid Donald Johanson, which got its name from the discoverer of the Lucy skeleton. It was just this past Easter, actually, was when the flyby happened. So on April 20th of this past year. But it's going to reach the first of the Trojan asteroids in 2 years, in 2027. It's going to hit Eurybates, which we have since learned actually has a binary called Keta. But it's also going to visit Polymele, Lucas, Oris, and then a binary asteroid system, Patroclus and Menoetius. So it's going to visit in total 1, 2, 3, 4, 5, 6, 7, plus a couple of satellites, which is far more than any other asteroid mission has visited. So,
what's your role? Yeah. What are you going to be doing? Or what have you been doing?
So I am involved. So my involvement comes from the fact that Dan Britt, my old thesis advisor, is the head of uh, the interior and bulk properties working group, which is basically to kind of try to understand, density, porosity, the bulk structure, and any kind of interior stuff. And he is not that far from retirement. So, space missions are long-term things. And so he kind of realized that he's going to be, retired and, enjoying Hawaii or something before the mission is done. And so he wanted a successor. So my job at the moment is basically to sit around and wait for him to retire.
But you're following along, sort of
But
learning from him
but
what
I
to
am
do.
following along. I attend the meetings. The neatest thing is when we have these encounters, then I'm on the telecons while these encounters are happening. By the way, missions are basically 90% telecons. Uh, but so when, for instance, when it passed Dinkinesh is a very interesting thing because it has its own little satellite, but the satellite itself is a contact binary, which means basically it's two lobes that are stuck together. Um, and so when we first saw the image of that, we were like, wow. And, it was just really cool to be, well, not in the room, but, on the telecon when those first images were coming out and to see it and go, wow, I know something that hardly anybody else ever knows. Yeah, won't know until, a few days from now. And so that was just
Fabulous.
really, really cool.
A couple of things on the nomenclature. They're called Trojan asteroids. Where did that come from?
Well, from the Trojan War, basically. And in fact, the names of the asteroids themselves, so Eurybates, Polymele, Lucas, Orus, Patroclus, Minucius, those are all, from the Iliad. They're, um, they're major players in the Trojan War.
Okay.
So,
And as I understand it, the Trojans are all in one group and the Greeks are all in the other group, with one or two exceptions.
actually, I'm not sure about that. Oh, that
Okay.
was not something that ever came up.
Okay. Well, another thing that came up, you've got this rock music connection. So have you been able to meet, or anybody in the group ever been able to meet any famous rock musicians? Because you've got an asteroid
Well,
mission named
yeah.
for a song.
So there's actually a rock musician who is a member of both missions, actually, OSIRIS-REx and Lucy. His name is Brian May. And in fact, I am a co-author on a paper that he's also a co-author on. So, but
For
Brian
those
May
of us of
is
a
the
certain age,
guitarist
remind us who
Brian
Brian
May
May
is the
is.
guitarist for Queen. And he also is an astrophysicist, and what he kind of specializes in is producing stereograms. So, you get two images from slightly different directions. And you can create a 3D model or a 3D image. So he creates these stereograms that we can use to kind of get more information about the actual shape of the objects. Um, and they're pretty cool. Yeah.
That's, of course, he's not the only member of rock star that has been visited by members of the science team, as I recall.
You're thinking of something I'm not, so
Okay, I think Hal
fill it in.
Weaver's at one point was showing pictures where he actually got to meet Ringo Starr.
Oh yeah. Yes, that was some years ago. I totally forgot
Yeah.
about that. Sorry.
And the interesting thing, of course, is Hal is about 6'5" and big in every dimension. And Ringo, like a
Yeah.
lot of kids who grew up malnourished during the war, is a lot shorter than people realize, especially now that he's in his 80s. So
Yeah.
you really have met some rock stars of the planetary science
Yeah.
field.
Yeah.
Now,
By the
the
way,
last,
in it just I in other kind of semi-celebrity sort of way, one of the nice things about the Lucy mission is that they have strong connections actually with the anthropology stuff. So we actually had Donald Johanson as a guest speaker at some of the science team meetings. So he talked about his experience uncovering the fossil. And a year ago in November, the Lucy Science Team meeting was at Arizona State, and we held it in the building that houses the skeleton. So,
Very nice.
yeah.
Very nice. Well, I'll end with a few more sort of what is in your immediate future? What brings you to the United States right now?
Well, what brings me to the States is basically well, I came basically for Thanksgiving with family, but I'm staying through until the Acme program in a week or two. So that's the this program. Well, you can describe it better, but
Right.
For Catholic educators.
And I think everybody here is
And
sort of a lot of the people on this will actually be at the Acme program, and almost everybody's heard about it since it's something that the foundation is supporting. Um, what about your future science? What do you have ideas of what's due in your lab, and what are you hoping to do in the
Okay.
immediate future and maybe the long-term
New in the
future?
lab, we actually just got a new structured light scanner. So it's like the laser scanner, except it doesn't use a laser. It projects a pattern of light on the specimen and then takes photographs and creates a shape model in the computer. But it also takes full color photos, which then it projects as texture onto the shape model. So we're using this to create a 3D catalog of the meteorite collection. And in fact, I'm going to be bringing the computer with me to the Acme. So anybody who's interested and who's going to attend can see some of the models that we're doing. But the idea is to actually create a 3D catalog of the meteorite collection, and that'll help better document it. But also, it'll be something that we can make accessible to other people to look at the meteorites in the collection. So,
Well, what's the science that you get out of knowing the volume?
well, yeah. So just like with the laser scanner, it's useful for measuring bulk density because you get the volume of the specimen. Actually, the same software that creates the shape model also spits out a volume. So
So you
which is
mentioned that
really
you're putting together this catalog of the Vatican's meteorite collection, which is what, about 1,200 meteorites at this point?
Yeah, 1,200 meteorites, yes.
And that comes to the one last thing I'd like to bring up that you've been doing. One of your jobs is curating the meteorite collection, but that means that you've become involved with the other curators of meteorites around the world. And can you tell us a little bit about what that sort of informal organization is, what you're doing, and what's been going on with them?
Well, for the most part, it is an informal organization that, we're not doing a lot as a group structure. We do gather at meetings, and occasionally we host a meeting. So at the Meteorological Society meeting in Brussels, there was a year ago, there was a a workshop before the meeting that was curation workshop. And that was the successor to a meeting that I held at the Vatican Observatory back in 2018, which was also a very successful meeting. And one of the outcomes of that meeting was we produced a document that basically sort of, all of the curators together kind of saying, here's what we think are the publications should be adhering to in terms of authors should specify the specimen catalog number and source of the meteorites that they're using for their research, which not only is good for giving the curators and the collections credit, but it's also, if somebody else subsequently wants to study that same specimen that somebody else studied, then they can track it down.
One of the things that I realized 30 odd years ago when I had your job, I started making samples of the meteorite Cassini available, which is a very, very rare Martian meteorite. And after a while, I realized that for the last 30 years, more than half of the publications of measurements of that meteorite have been measured on our same specimen over and over and over again. And while we're happy that we're able to do this, this is also possibly a problem that people keep looking at the same one specimen thinking that it's the perfect example and that every piece of Cassini is like this one. And if you didn't pay attention to which specimen was being measured, you might not realize that.
Yeah. Yeah, so that is the other side. Maybe some people want to study the same specimen, but maybe they want diversity, so they want to study other specimens. Of course, you have to be careful not to use the term diversity in your paper.
Right, then they won't let you publish it. Well, we've come to the close here, and so I'll ask you one simple question. In your dreams in the next 5 years, as a meteoriticist, what would be the one thing you would love to be able to accomplish or love to be able to do?
Well, not so much about accomplishment, but in terms of my own personal development, I'm really interested in learning more about spectroscopy and meteorite spectroscopy because, quite frankly, a lot of data comes out of that, and it's not something that I ever had any formal training in. So I'm actually, I've got some connections of I might do a sabbatical where I do some intensive learning about spectroscopy and learning how to interpret the bumps and wiggles that are in a spectrum. So that's what I want to do for myself. In terms of actual results or studies, we'll see where that goes. I'm not thinking that far ahead.
Okay. One of the questions in the audience here from Dina is, does this 3D scanning connect up with your 3D printing? Because she knows you're a great fan of 3D printing.
Sometimes it does. So there's two things I like to do. So sometimes I'll create a 3D model of the meteorite if it's got some interesting structure. Or like we also have 3D models of some of the OSIRIS-REx specimens. So I 3D printed some of those just to put on display because we obviously can't put the real thing on display. But then also for creating mounts and cases for the meteorites if I need to put them on display or to pack them up to send them to somebody else, I'll do a form-fitting mount or form-fitting box that basically I take the inverse of the meteorite and sort of create a hollow that's the shape of the meteorite that I can use. So the 3D scanner comes in quite handy for that. Yeah.
Okay. Are there questions from anybody else in the audience before we pack up here? That being the case, thank you, Bob, once again for being part of this.
Can I ask a question?
Thank you.
Oh, yeah, Bill's got a question.
Oh, yeah.
Yes.
Yeah. One thing I find interesting about the Lucy mission is there's going to be a time starting in the summer of 2027 when because Lucy's passing through a group of Trojans, there's going to be like a year and a half where they have 4 flybys. And I'm wondering if you know anything about how the people of the mission are sort of steeling themselves to go through a really rapid pace of encounters. The first 2 were just like a month apart. So that seems like usually a flight mission or a mission has some time to relax between one set of observations and the next.
I mentioned that 90% of a mission is telecons. So there's been a lot of preparation going on in these telecons and in offsite stuff. So yeah, there's a lot of front loading of the work that goes into these things. And also, by the way, the flybys are going to go quick, but much like with the New Horizons mission to Pluto, which, by the way, Lucy uses a lot of legacy stuff from New Horizons. and so, but much like that, a lot of the data is going to be kind of stored and sent later. So just like with New Horizons, kind of you get the quick and dirty stuff, the images and stuff, but then a lot of the other data it kind of comes down the pipelines as time is freed up. So, by the way, this communication lag that I mentioned, the demand for terabytes versus the kilobytes that you actually get. There was recently, I think it was the Juno mission, tested a laser communication system that they were able to transmit video in real time. So they had stored a cat video or something on the spacecraft and transmitted it back to Earth. That is a game changer. That is an absolute game changer for future missions.
Yeah, that was the Psyche mission, I believe.
Oh, the Psyche mission, yeah.
Fabulous. Okay, well, we are coming to a close here, and usually I like to be able to get people off before the end of the hour. So maybe time for one last question, if anybody has anything. And if not, I'll see many of you at Acme next week. All of you, I wish you a wonderful new year, and we'll see you next full moon. Thanks for coming, everybody. And thanks again for Bob for giving us your time.
My pleasure.
Thank you, guys. See you next time.